Hello and welcome back to Calculus 1, section 2.5, limits at infinity. Well, this is obviously different than infinite limits. Now we're looking for the input to be infinity and the answer to be the whole number if possible. So now we are looking at the, hold on, there we go, limit x goes to positive or negative infinity of f of x to give us L being a finite number. Well, that L could also be infinity or does not exist as well, but we are going to focus first and for the most part on L. So this is what we're looking for. Example, good old 1 over x, and we look for the limit as x approaches infinity of 1 over x, and as you look at the graph you see that your x approaches positive infinity, the answer approaches 0, the y value approaches 0, so the answer is 0. Do we all see that? As you are walking towards infinity in x, the y value, each point, as you are going towards infinity. What do you mean going to infinity? Well, here, then here, then here, then here, and you are marching towards infinity. You see that the y values drop, and they drop, and they drop, and they drop towards 0. Y equals 0. Another example, f of x equals e to the negative x, the decay function. You studied this in your pre-calculus course for the radioactive decay, garbage decay, and other problems, right? The carbon dating and so on, metabolizing drug in the system. We've seen earlier Advil, right? When I demoed Mathematica, you have seen 1.9 hours biological half-life to metabolize in the system. That means that every 2 hours, roughly, the amount of Advil left in the system is cut in half. By this graph, by the graph of a decay function, it actually never goes away. You have to wait infinity for it to go away. This would be the initial value, let's say dose of Advil, and then you would have your time axis. We call it x now, but that could be the time axis, and you see that the amount of drug, not just Advil, anything that you put in your system, is decaying over time. Now, what happens is, in the 2 hours, half of the dose is left. So let's say it's a 200 pill, right? You wait 2 hours, now you have 100. Then you wait another 2 hours, you have 50, and that's 4 hours. You take another dose, so now it's 250. And then you wait 2 hours is 125. You see that? Technically, every time you take a dose, you're increasing the amount in your body, because the old stuff is not gone, right? The old stuff is not gone because it's always divided by 2. Half-life loses half of its mass. So this is what decay means, which is why the plastic bags in these bottles are decaying for 10,000 years or 20,000 years on a pile somewhere. So I'll erase this stuff. So you can go research those things. Now we're going to take the limit as x goes to positive infinity again of e to the negative x, and we are going to find another big fat 0 here. But again, you have to wait for the infinite time, right? So this is what we are talking about now. You are observing these limits as they go to infinity, and you hope to end with the value L. Now let me also give you an example of situation when it's actually some kind of number. So logistics growth in exponential functions is used to realistically depict the population of humans or rabbits or bacteria, whatever. So logistic growth, and if you look at the graph, you are going to have initial population P0, and you are going to have exponential growth, and then it's gonna even out, and then it's going to approach this value K. Well, that's actually the L we talked about. Now, what is this all about? Well, first off, in pre-calculus you studied the concept of population, and you used e to the kt, right? P0 e to the kt, whose graph was like this. Now, if your IQ is bigger than 7, you know that that's a garbage model, because for infinite time, you would end up with the infinite population, which is not possible on the planet that has a finite surface area. You cannot fit infinitely many population of anything on the finite surface. So, I mean, without going into details, when you look at this model proposes carrying capacity K, which is the maximum amount of population that you can have, which cannot be exceeded because of A, finite area of the planet, and then B, finite amount of resources. There's just so many minerals and things that are in the ground that you can exploit before you use it all up. So the question is, you know, for scientists to agree whether the number is 10 billion or 15 billion people. Either way, we're doomed because we had 7.4 now. Doesn't really matter whether it's 10 or 15. Just give it another 20 years and there you go. The limit in this case, so the limit of f of x in this case would give you this k as x goes to infinity, because you have your so as x goes to positive infinity, you see that the y value settles at this k. Now clearly, in terms of the population on Earth, when you don't have resources, the resources are scarce, then we start competing for resources, if you know what I mean, right? So exponential growth, we are right here, right now, that's where we are. And then you just wait another 20, 30 years, and then we are getting into the competition mode. So, which is why Elon Musk wants to get the hell out of here, right? He's investing all of his stuff into the rockets, so he can, you know, maybe bring one of you, and that was so he can still be superior, obviously. Absolutely no other reason. He's not going to go by himself, right? So we have logistics growth, and you see that all of these examples that we covered have x goes to infinity, and then there is an answer that we hit. And that's it. So now let's talk about the application, which is horizontal asymptote. horizontal asymptote, we are going to write the red stuff again, which is the stuff you learn. A function f of x has horizontal asymptote at y equals L if the limit x goes to positive, negative, infinity of f of x is equal to that L. So, our previous examples, limit of 1 over x as x goes to infinity equals 0, implies that there is a horizontal asymptote at y equals 0. That was the example. Limit of population function in time as time goes to infinity, doesn't have to be x all the time, is equal to carrying capacity k, which means that the horizontal asymptote at y equals k, carrying capacity. That was the third example. Now let's take a look at some examples from homework. Say you have a limit, x goes to infinity, of 3x squared plus 1 divided by 2x squared minus x minus 2. I put whatever. Now, some of you might remember the 3 rules from pre-calculus for horizontal asymptote, and those were related to the exponents of numerator and denominator. Does anyone remember those rules? You can see the enthusiasm and eagerness to answer this question. You forgot them because who cares? And yeah, exactly. Because remembering the 3 rules which apply only to rational function when there is a book with 2,500 pages of other functions, it's very inefficient. So, no, you don't have to sit and relearn those because they only cover rational functions. Rational functions are these: polynomial divided by polynomial. Remember, you have a square root functions, you have a linear function, you have a quadratic function, you have polynomial functions actually, exponential, logarithmic, trigonometric, hyperbolic. There are going to be functions all over the place. Do you really sit and memorize all of them? No. You learn the red rule. And then if the red rule is satisfied, you have horizontal asymptote. If a red rule is not satisfied, no horizontal asymptote, move along with your life. It's very simple. So what are we going to do here? The trick is to divide by the highest exponent from the entire problem. You see x squared and another x squared. So x squared is the largest. So we are going to divide everywhere by x squared and then fix algebra. So that's going to be limit x goes to infinity, and now I have 3 plus 1 over x squared, 2 minus 1 over x minus 2 over x squared. Then I'm going to write the step that you will never write after this time. By properties of limits, you know that each individual term gets its own limit, x goes to infinity. So you are taking a limit of one function and actually making this into a problem of 5 separate limits. You have the limit x goes to infinity of 3 plus limit x goes to infinity of 1 over x squared. And then you have 3 of these on the bottom in denominator. So limit of 2 minus limit of 1 over x minus the limit of 2 over x squared. So now we are going to discuss limit of 1 over x to the power p as x goes to infinity. And as p is bigger than 1, right? Let's do the experiment together. Behold number 1. One piece of paper, right? And I want to see what happens as I divide this by a larger and larger number. When I divide by 2, the answer, which used to be 1, becomes a half, right? So as you divide 1 by 2, you get a half. Now, if you divide half by 2, the answer from the original start point will be a quarter. Now, hopefully you agree that this is smaller than the entire paper when we started. Divide by 8, divide by 16, divide by 32, divide by 64, 128. What is happening? What is happening as the denominator went from 2 to 4 to 8 to 16 to 32? What is happening as the denominator is going to infinity? What is happening with the answer? Where is the answer going? It's going to 0, right? If I keep dividing this paper forever, gone, right? So, this big formula over here that is going to stay with you for the rest of your life says this, and if we know that, then 3 of these limits are dead instantly. Limit of 3 is 3, limit of 2 is 2, so the answer is 3 halves. Now, if you remember your pre-calculus, in pre-calculus they said, if the exponents are the same, then the horizontal asymptote is at the ratio of front coefficients. Yeah, there it is, right? Without memorizing that rule. We took the limit and we used this fact, which we just seen, that works, and we got the answer. So, if you have a rational function, your job is to divide by the highest exponent, and then any limit that goes and cancel any limit that goes number over some exponent of x that goes to 0 by the big red formula. And then if you have anything left over, well, you work with that. This also clearly works there, because this exponent over here is x to the 0 and this is x to the 1. So bigger exponent in denominator and you get 1 over x, and then by the red formula it goes to 0. So you can do these limits one by one. I believe they have interesting example. Let's see, 2.6 and then go one back. I think, yes, there we go. Beautiful. So, problem number 30 is interesting. It says, limit x goes to negative infinity, and then we have 40x to the 4 plus x squared plus 5x divided by the square root of 64x to the 8 plus x to the 6. This is a trick question. What is the highest exponent in the problem? 4. Square root of 8 is 4. So x to the 4 is the highest, because the square root of x to the 8 is going to be x to the 4. So we are supposed to divide everywhere by x to the 4. That's the reason why I picked this problem. It's different than other problems. And then we'll do one more, which is also very interesting. So I'm going to now use the red over here to divide everywhere by x to the 4. And I am dividing the entire denominator with the x to the 4. When that x to the 4 undergoes the square root, it will become x to the 8. So we have the limit, x goes to negative infinity. So now a little bit of algebra over here. We have 40 plus 1 over x squared plus 5 over x cubed. And now we have square root, I'll write the step, 64x to the 8 over x to the 8 plus x to the 6 over x to the 8. Let me just put this on a side, just in case that you are not seeing it yet. Guys, when you have a square root of, let's say, 3x to the 6, or let's go with 5x to the 6. This is equal to x cubed root 5. Now you can stuff this back into the square root, and you better get 5x to the 6. So if you are escaping the square root, the exponent gets cut in half. If you are stuffing things in, you're stuffing expressions into the square root, well, it's going to pick up exponent double. If you are stuffing into cube root, then it's times 3, and so on. So what I did is I stuffed this x to the 4 under the square root and became x to the 8. So now I have the limit. X goes to negative infinity. The numerator stays 40 plus 1 over x squared plus 5 over x cubed. And then in the denominator I have a square root of 64 plus 1 over x squared. Now, dead, dead, dead. Because of the red formula. you are left with 40 divided by square root of 64, which is 5. And the limit is 5. So, be careful when you have square roots and cube roots and those guys around, because that will adjust the exponent that is under that root. And that's that. Let's take a look at problem 20. This one is really cool. And it's cool in my book. You might think different things are cool. So problem 20 from the textbook says the limit x goes to negative infinity again. Nice. X goes to negative infinity of 5 plus 100 over x plus sine to the 4 x cubed divided by x squared. I love it. So you probably went, yeah, easy-ish. Sine to the 4th. Holy nightmare. Well, do not fear. Sine is bounded by 1. It doesn't matter what is there and what exponent you put on sine. If the maximum value that sine can ever reach is 1, and you raise that 1 to the 4th power, or 400th power, you're still going to have 1. The numerator cannot exceed 1. That last term there is technically 1 over x squared, which dies with that red rule, like this. So you just get to ignore sines and cosines when they appear within these limits. Well, if they appear in a different way, then you have to acknowledge them. But when they get divided by the polynomial, they just die. So this thing over here is now going to be, because it's raised to the even exponent, the value of the number in the numerator is between 0 and positive 1. When you divide that by infinity, you are getting 0. So, dead, and the answer is 5. Ooh, it appears that every answer is 5, right? It's not. That's problem 20. Now, if you want to know why, sine and cosine are bounded -1 sine x +1. So at most, what your expression can be in the numerator is 1. When you divide 1 with infinity, you get 0. The next application of these limits at infinity, well, actually no, before I go to the next, let me just talk more about, so all of these have horizontal asymptote at y equals 5, horizontal asymptote at y equals 5. So when you get a finite number, by that theorem we had earlier, definition that we had earlier, the horizontal asymptote is at L, which in this case is 5, and then the second example, 5 again. Now, horizontal asymptotes are not as powerful as vertical asymptotes are. Vertical asymptote can never, ever, ever, ever be crossed by a function. Vertical asymptote cannot be crossed, ever. Horizontal asymptote must be obeyed at infinities, which leaves it vulnerable in the middle. Functions can pierce through the horizontal asymptote. This will be reinforced when we learn 4.3 later in 2 months, let's say, in a course when we learn 4.3 graphing functions by hand. We are going to see the function that would look like this. So let's say you have a vertical asymptote and another vertical asymptote, and then you have a piece of the function here and a piece of the function there. I am going to draw horizontal asymptote in red and point the arrow and say ha at y equals 0. So you see vertical asymptotes, right? I don't have to emphasize those vertical lines. Those are vertical asymptotes from last lecture. The red line is the horizontal asymptote we just learned. We are going to run into an example that is going to cut right through the asymptote, and that it's okay. So let me write that here in blood. Horizontal asymptotes can be crossed locally. Horizontal asymptotes must be obeyed at positive and negative infinity. So you see the function follow horizontal line at negative infinity and positive infinity. That's never going to cross there, but in the middle the function can cut through. So learn this now, remember it now, so that when we get to chapter 4 you're not going crazy with what the hell is going on. This is an asymptote. Why is the function going through? What am I doing wrong? What you're doing wrong is not learning stuff now. That's all you did wrong. The rest of the problem you did right. You just don't understand what it is because you haven't learned. Right? So learn. The last pre-calculus concept, which is related to our limits at infinity, is what we call the end behavior. End behavior of the function has those 4 stages. So here's the chart. I'll move the chart here. Function could have this type of a behavior. Please note that this motion is going to positive infinity in x and positive infinity in y. So it shouldn't take a lot of IQ to write that the limit x goes to positive infinity of f of x is positive infinity. This is the end behavior, and one of the possibilities you can have for a function. Another one would be looking down, where we write limit x approaches positive infinity of f of x gives you negative infinity as y because it points down. And then just fill the other two. Limit x goes to negative infinity of f of x is positive infinity, and limit of f of x as x approaches negative infinity is negative infinity. This is what it's known as end behavior. This allows me to analyze, let's go with it to the negative x decay function. When I draw a decay function, I have two ends. I have the red end. At the red end is the limit of e to the negative x as x goes to negative infinity is positive infinity. That is the end behavior, showing that as you go forever negative, the y value will go to positive infinity. And then we have the blue end on the other side, which is actually the asymptote, because the limit x goes to infinity of e to the negative x is equal to 0, which implies ha at y equal to 0. Some functions are born of end behavior, some of asymptotes, and some of combinations. So e to the negative x is clearly a combination of end behavior on one side and the asymptote on the other. Yes? This? So now I want to draw a few more examples well, in particular, one example that is very important, and that is inverse tangent. You absolutely must know this function, otherwise some of the steps in the future are not going to go too well. So f of x equals tangent inverse of x. So this function has horizontal asymptotes at negative pi over 2 and positive pi over 2. And the function looks like x cubed function, sideways, right? There we go. Remember this graph. It's gonna pop up as you go on through not just Calc 1 but later courses in math and science. So the red one says that the limit as x goes to negative infinity of inverse tangent of x is negative pi over 2. Yeah, that's your horizontal asymptote. And the other side also is a horizontal asymptote. Limit x goes to positive infinity of tangent inverse of x is positive pi over 2. So here is an example of a function that is squeezed in, sandwiched in between two horizontal asymptotes. It's not the only function, right? Cotangent is also squeezed in between, and there are some other functions also in mathematics that are squeezed between these multiple asymptotes. So this is it. Two more things. One is, remember how I said sine and cosine are bounded by 1, and so you have to distinguish now. If you have a limit x goes to infinity of sine x, the answer is does not exist, because sine x and cosine x, and for that matter tangent and so on, these guys are periodic functions. So they don't settle at a value as they progress. Sine is the infinite wave, right? And if this wave goes to infinity, well, it doesn't really stop ever. So at infinity, it assumes all of the y values between -1 and 1, and we know we can't have that. So there is no finite end value that it's either 0 or 7 or infinity, because sine oscillates between -1 and 1. So if you only have a term with a sine, well, there is no limit. However, if you have limit of sine x over x as x goes to infinity, the answer is 0. Because in this case you say, well, sine is bounded by 1, and then when I divide 1 by infinity, I get 0, woohoo, right? And you move on with your life. So this is the situation that you have to be careful about. We did have this sine to the 4th divided by x squared, and that was 0. Because sine was 1, 1 to the 4th is still 1, 1 divided by x squared is 0 by the red formula we had, therefore that's that. So you just have to be careful, right, with these type of things as you go on. And now let's talk about, wrap up these 2 lectures and talk about application and stuff that makes you happy, right? So, many issues in design arise with inability to spot infinities, singularities, and things like that. Any buildup of energy in a short interval of time is a recipe for disaster. When you are trying to either compress or release insane amounts of energy, you are getting either a fusion or a fission, which is the mushroom, right? Well, not with a fusion, but with a fission, right? So in certain areas of research, like mathematics of detonation, which is actually a mathematical field where mathematicians sit and design bombs, that outcome is desired. But if you're designing electronic equipment, you do not want to have whatever the Samsung or the Sony had in the past, where you pick up the device and it goes kaboom, right? So when does this happen? Well, it happens with asymptotes. So if your design calls for certain things, and there will be another section in Calc2 that is very important from the design perspective, improper integrals. You have that the current is equal to the voltage divided by resistance. This is called the Ohm's law in physics. And the current is the flow of electrons, and that flow of electrons gives the kinematics, right, the motion, and gives the energy to the system that you want to have working in this electrical realm. Voltage, which is, you're used to 110, it's actually 118, and it drops down to 110 when you plug something in. So the voltage of 110 volts is the potential that drives the motion. Just like when you have a pipe and you see that the flow happening, because when I lift this part up, I am creating difference in potential energy. Right now, this energy here of this end is higher than potential energy of this end, because mgh, mass times the gravity times the height. Bigger height, right? Gravity is the same, mass of each particle is the same, so it's just the height that is the difference between these two for potential energy. Everything in nature is lazy. It tends to the state of the lowest energy state, which is the reason why our planet is round, not a disk. There are imbeciles that are thinking that the Earth is flat, and that to me in today's day and age is, I just can't believe. By the way, imbecile is a medical term which describes the IQ, so it's perfectly fine to use in this context. So the lowest energy is the state that everything tends to. So now, where is the lowest energy state? Well, if this is a higher potential than this side, then more energy here than there, so water wants to be here. If I try to trick the water and bring this up, the water will say, yeah, bye. See, moves here, because this is the higher and the water wants to be lazy at the lowest energy state. So this flow of water that you see is because of the difference of potential. Wind is another example where you have difference in atmospheric pressure. So you have the pressure with the area with bigger pressure than the area with smaller pressure, and the air says bye, because I want to be at the place where there is a lower energy state. So the voltage is this difference of potential which makes electrons move to get to the place where it's a lower potential. They have lower energy and they're happier in that state. So voltage gives current in motion. It's like a fuel for the motion of electricity. And the resistance is going to be the how much stuff you can fit through the hose or through the pipe. Obviously, more resistance means it's smaller, so the less stuff can seep through and things like that. So now, when you understand that, you have that the current is equal to, let's say, 110 volts divided by resistance. What happens as you short the outlet? Take the piece of insulated wire, stick it inside, and it goes boom. Why? Well, what you did with a short piece of wire is you are making this to go to zero, which makes this try to go to infinity. There is your infinite buildup of energy in a short amount of time. Now also, current is proportional to temperature, which means bigger the current, more temperature. It's hot too, right? So all of these link together, and now you have the reason why you don't want to design stuff that is going to be shorted at any point. You don't want to cause short circuits, because in our houses that are made out of wood and cardboard, obviously, right, the big bad wolf comes in, puff, and there's no house, right? Which is electricity, little spark. And so just get the licensed people that know what they do and they have insurance, right? And don't try to, rig your stuff. Oh, the fuse keeps popping up, so let me just change 15 fuse for a 20 because I want to have 17 things plugged in the same outlet. Well, guess what? Your wire in the wall is still 15, so you can put 150 fuse on it. When your wire is still 15, your house is going to burn down. Yes, it will. So, public announcement over. All right? Yes?
So, I then becomes a limit as well as R. Technically,
yes.
In that.
Well, the I becomes so this is actually the
limit approaching infinity. Yeah, yes. Yeah, and then the R becomes a limit.
Yes. Okay. So this is the answer. We are used to have this on the other side. But yeah, so this is the vertical asymptote example where you are shooting into the vertical asymptote with a zero and it goes skyrocket, right? And that's that. And then, as I said, temperature and current race together. So as one tries to get to infinity quickly, the temperature tries to get to infinity quickly. Your breakers are designed to quickly shut off these situations. So. Another thing is that the outlet, the GCFI or GFCFC, whatever it's called. In the bathroom, you have the outlet, and it's special with those two buttons, right?
Yeah.
So that burns out, and the people say, well, let me just put the regular one in. No, right? Because it has a little switch inside to disconnect, because that's this close to the water over there, right? Distilled water doesn't conduct electricity, which is always funny when you see a lab on fire, right? And then they say, oh, electricity in distilled water. No, it's the minerals in the water that conduct electricity. So your tap water is going to conduct because it has all the pollution that is in it, right? Where if you buy the distilled water and you put the current in it, you stick your finger in that happens. But the bad tub, yeah. Alright, cool. Done.